This is a table from the book. First off, near the Earth's surface, typical electric field is 100 newtons per coulomb, and it's directed down. Now, that doesn't seem so large, 100 newtons per coulomb. Here's the thing. Over a distance that's equal to your height, that corresponds to a difference in voltage, which is something you have some sense of about 150 volts. So I'm saying to you that outside, in the air, there's a voltage difference between your head and your feet of 150 volts. And so you might ask, why is it that you don't just step outside and experience a tremendous electric shock and like fall screaming to the ground, which would be cool for me to watch people leave class. Why don't you experience that, okay? And we'll talk about that in terms of the motion of charges. But there is the electric field, and it's actually pretty big. It's actually pretty big. Electric fields near objects charged by rubbing, 10 to the third to 10 to the sixth newtons per coulomb. That's quite a bit bigger than that. Why does it only go up as high as 10 to the sixth? Because if it goes up as high as 10 to the sixth, that's big enough to cause a spark in air. When you pull tape off a roll, this is how big the field gets. It gets that big because if it gets any bigger, it causes a spark to jump, charges redistribute, and that cancels out some of the field. And so it gets as big as it can be without making sparks, and the sparks fly, and it kind of like bats it back down to that level. The Van de Graaff generator, which we saw last time, I'm going to take a quick peek at this. We've got the Van de Graaff generator, and if I turn it on, it builds up a charge on the surface, negative charge here, and I'm going to have an electric field near it. And when the electric field gets big enough, what it does, it actually tears electrons off of atoms, tears electrons off of the atoms. Oh, then all of a sudden the air is ionized. It's made up of positively charged ions, negatively charged electrons. The air ceases being an insulator, begins being a conductor, and a spark jumps between the two. And so the electric field, there I'm getting up to 1,000,000 volts per meter. Oh, yes, and it's turning off the other projector. Oh, yeah, we'll have some things to say about that. Turning this off, which is kind of cool. Here's the thing, though. To make this happen, to make a spark jump, this is kind of a pretty dramatic thing, but you can make this happen on a much smaller scale in different gases. On the front table, I've got this device right here, which is it's a fluorescent light bulb, and it's connected not to an ordinary power supply. It's connected to a camera flash. And that thing puts a voltage between these two electrodes. Current would like to flow from this electrode to this electrode, but it can't because in between charges can't move because the gas inside here, which is mercury vapor, is an insulator. The charges are not able to move unless I was to take some of the charges and strip them off of the atoms. I have ionized mercury atoms and free electrons. And guess what? I have charges on me because I've been standing near the Van de Graaff generator. I'm charging. Oh, yeah. And my electric field, big enough to tear electrons off of atoms. Sweet. There we go. And actually, the electric field around me is big enough to cause sparks inside there, which is cool. Oh, and if I take something and I rub it with a cloth, oh, yeah, even more charges. Oh, yeah, and so I can create a big enough electric field near here to cause sparks to jump, basically, inside here. And so what I'm doing is I'm making an electric field big enough to rip molecules and atoms asunder. Sweet. That is really fantastic. So that's a little bit about the electric field and the kind of magnitudes you have. And we're going to look at cases of doing things like this. The electric field near here, 10 to the sixth, enough to make these kinds of things happen. I want to look at some examples of deducing electric fields, and we're going to do it by looking at charges. Remember, we talked about how to deduce what the electric field is. You imagine that little test charge. So do this. Consider the electric field at the point noted by the small black dot, in which case is the field at the dot the largest, in which case is the field at the dot the smallest. Talk to your neighbors about this. And I'm going to come back and ask you to vote on this in about 30 seconds. So go ahead and talk to your neighbors. All right, let's take a vote. Where is it? Let's do the largest. Where is the field the largest? C. How come point C? Biggest charge, smallest distance. Does this problem look like anything you've seen? Wasn't there the exact same problem last time? However, I just copied the slide and then I changed the text to read. Last time it read, you put a small positive charge here. Where is the force the largest? Where is the force the smallest? Now it says, where is the field the largest? Where is the smallest? But how do you determine what the electric field is? You imagine a small positive charge there, and you deduce the force. So this problem is identical to the one that you saw previously. That's how we deduce the electric field. Imagine a small positive charge there, and it's the force on it's biggest here because it's a big charge and it's a small distance. It's a small distance. Now, how about this one? Again, similar to what you've seen before. All the charges in the diagram are of equal magnitude. In which cases is the electric field at the black dot to the right, to the left, or 0? Talk to your neighbors about this, and I'll call for a vote in 30 seconds. You can speak in a normal tone of voice, too, if you'd like. Okay, there's one case that's to the right. Which one is to the right? B. B, because imagine small positive charge here. It's repelled by this one. It's attracted by this one. Which dominates, the attractive or the repulsive force? The repulsive because closer. And so this one is going to be to the right. How about this one, right or left? Left. This one, left. And this one, 0. Because I've got force to the left, force to the right from those two charges. They're equal magnitudes, and so they're going to cancel. So the electric field at that point is equal to 0. Let's look at a more significant case here. I'm going to look at this case. It's what's known as a dipole. And it's called a dipole because it's got two poles. There's like the positive and the negative. And it's reminiscent of a dipole magnetic field. Positive charge, negative charge. I got 3 points. Point 1, point 2, and point 3. I'm going to call names out of the box. And I want you to tell me at point 1, and then point 3, and finally at point 2, what is the direction of the electric field at these points? What is the direction of the electric field? I'm going to call names out of the box to tell us. What do you say for that point? Think about the thing you just did. So first up, let's do point 1 up, because it's going to be repelled by this one. It's going to be attracted by that one, but the repulsion dominates the attraction. And so the electric field at this point is going to be up. It's going to be up. How about at point 3? How about at point 3, below the dipole? If you imagine putting a small positive charge here at point 3, it's going to feel a force from the negative charge. Which way, up or down? Up. It's going to feel a force from this positive charge, up or down? Down. Which dominates, the upward force or the downward? The upward force. So what's the direction of the electric field at this point? Up. Up, up. So at point 2, what's the direction at point 2? Down, down. Because I imagine this one, if there was a positive charge that points in that direction, and for this charge, I'm going to get a vector which points that way. And when I add those two up, downward. So I get an up, I get an up, and I get a down there. And those are the field vectors from a dipole.